Today I'd like to do a review and a slow review so that you can ask questions about the one oscillator being forced by an outside force that's very weak but capable of creating a big resonance. And then we're going to do what we kind of did at the very beginning of this when we started the classical section. We talked about bangs, and it involved two, super balls, but first it was two cars. And that's what we're going to do with this. Only this time the transfer is going to be by resonance rather than punch. And the idea is that's the simplest way. We've already mentioned this a little bit, and the problem that I've given you with two phasors and then two spaces, position and velocity, is exactly what you need in order to chart the motion of the resonance that we'll talk about today and for a couple more times, because this is the key, so if you say the root of what we call modern quantum mechanics. Quantum mechanics, it wasn't just kind of a weird contrivance built on top of classical mechanics. And that was the thing that Einstein, Rosen, Podolsky, and a few others were working on very hard. And it went a little bit, and we'll get a chance to talk about that later on, but it would have been a failure if that's all we had. The actual building of things like the Schrödinger equation, which is what this really is. We'll be looking at the simplest Schrödinger equation by just studying this device right here. Okay, now the mathematical methodology. First, geometry. I'm going to make a solution and give you a feeling for the motion of this, right down to the problem of how the phase is, particularly pi over 2 phase, plays a role in the dynamics. But also the algebraic solution, the algebraic way of solving the matrix that describes this system. We have some really neat ways to do that make this less of a chore and more fun. And in this case, I'm going to take a very simple matrix, 1, 2, 3, 4, which has nice integer solutions for everything, and give you a feeling for the algebraic operation of matrix diagonalization is basically what it's called, but the idea of doing a spectral decomposition of a matrix, however large. And this 2 by 2 is the simplest case, non-trivial, but the thing that we'll be putting together here is a complete theory of spectral operators, things like that. And it turns out that that's a lot easier to do than the sort of half-assed ways of approaching the diagonalization that you'll see in a lot of textbooks. But first, let's look at the geometry, because that's, I think, important to understand what it is that's really happening. And one of the things that I want to make clear is the role that relative phase plays. And that's what I'm trying to get across in the first few homeworks, where we draw the double phasor in its spaces. But let's go back and see, as best we can, a review of what happens with just the single phasor, just the single oscillator, the single forced, damped, harmonic oscillator with the Green's function that we looked at last time. I want to look at pieces of that and give you a feeling for where things are. Now, you'll notice that forced and damped are not in any of these. So when I do this right here, I'm going to be making the assumption there isn't any friction and there isn't anything happening from the outside. Obviously there could be, and in fact the demonstration that I have has lots of friction. Unfortunately, you can't get rid of that. But that's this guy right here. The possibility of coming in and applying a force either here or both is certainly very much an issue. And if you never did that, we'd never be able to see what any quantum system did. But if you leave the quantum system alone and let it operate, as they say, autonomously, that's what we'll be describing here. And then the whole thing of looking at it, that's a whole nother problem. But the actual dynamics of this system is identical to Schrodinger wave mechanics, Schrodinger equation, all of that stuff that was what we call modern quantum mechanics, the beginnings of it anyway. Okay, so let's do the review of that. By that I mean, let's just look at this guy that we looked at last time. And this is a summary of that Green's function. I think I'll put it over there to start with. And then we're going to draw, let the computer actually draw, but I have already placed a drawing here of that function that's much nicer than the old-fashioned applications that I first built all this stuff with. The idea is that there's a real and imaginary, and then a sum of the squares of the real imaginary that's called the absolute value being plotted there and here. Here I believe the absolute value is plotted in black. It's hard to tell because there's so many pixels there. The real part of this thing, that's this function right here that we worked out, the real part of the Green's function, the response function. And that's what R is supposed to stand for here, response. And then the real part, the imaginary part of that. Forgetting about Mr. Green for a while. Anyway, the thing that's black there is overlapping all of these things is the absolute magnitude. Something that you're most likely to be able to measure as opposed to the more delicate parts of this response, which are the things that involve the phase. And the real part is the one that does a rather interesting little zigzag, reaches a maximum, seems to be cut in half by the imaginary part at that point, drops precipitously right through the natural frequency. And this is the same oscillator we used last time, 1 Hertz, and a damping, I should say a decay rate, a gamma of 0.2 exactly. Now, let's see if there's anything else I need to say. Yes, the imaginary part in both cases is being plotted in some shade of green. I think you can see it right there. And it is something that goes to 0 on either side of the resonant frequency. See here very clearly going down. But the real part does not. The real part just gets very flat as you move away from the resonance towards zero frequency. And if you recall, we gave a name to that particular response when the stimulus frequency is very near to 0. And that name is direct current response. That means no frequency or very low frequency stimulus. And the idea is that in this case of the mass here with the feather, that was really so small because the feather couldn't provide very much force. Where did the feather go? Here it is. The idea there was that I put this on there and then I bend it, and you can barely see that I have moved it. I can release it, and that's twice what I moved it. So that's the DC response, and for a long range of frequency going up to its resonant frequency, it's about a Hertz for that thing, it's not going to do much. This is a very flat function. So we're looking at this function right here. We're looking at omega 0 squared minus omega s squared divided by that quantity squared plus a little bit. And the idea is that this is a much smaller quantity here, and the gamma is 0.2. That's pretty small compared to the other numbers there. So this is going to be a flat function as I go up in omega s. It's not going to change until I get in the neighborhood of the big peak, in the foothills, so to speak, of that feature. Okay, so one of the things I probably ought to do is try to run a low frequency thing just to show what it is, and that is going to take a little bit of doing here because we don't have the links that I really need, but what I'll do here is back out of this and go over to the thing that has some of these things working. Now what I'm going to have to do is hunt for this a little bit here before I get it. Let's see where I can find that. I think what I might do, little thing, probably ought to do it on the other one. So let me go back here. We'll use this one as a sort of a reference. And try it on this one. Using Chrome, which I hope has it. Yeah, I think this has got it going. So what I'm going to do in here, first of all, I think I'll set it up on a view that makes it fairly large. So I'll hold up just a minute here. It seems to be working. Let me see if I can get it to. Let me just see if I can get it started here. Reset t equals 0. Resume. Yeah. So it's going, and what I'm going to do, just to make this, let's go full screen, make it a little bit larger. That means I've got to restart it. But here, a good thing to see is that if you go to the controls and then scroll down, we have several choices near the bottom here for forced oscillators. Eventually we would improve this so that it was like the old application and actually show the response function with some points that you can click on real quick to get it. But let's take almost DC and see if we can get that going here. Now, I'm a little worried about that. That's definitely not what I want. That is behaving very badly. I'm not sure what's going on there. May be out of business today. Yeah, that's not what it should be doing. I may have to use the old one, and that's really ugly. Let's see if it'll behave just for simple things like that. That's not behaving very well either. Although actually it's doing it. The other one is doing it right. I am not, a little puzzled here. I had these things working at home, but now it's not. We had to rescale the forces, and I think you put the scale factor on the wrong thing. Let's try resonance to see what that comes out to be. Now this is, that seems pretty close to right, although a few things screwed up there. We may have to take a bye today on this. This is not good. Let's try one. See if this works here. That one seems to be behaving. Let me not emphasize steady state, and let us run that, see what happens. Okay, reset time, and see if I can get this one going. Look at that one more time there. Let me set this up so that it shows the transients. That's what I really want to explain to you today. Reset time equals 0, and go. Okay, this is not exactly DC, but I'm going to go in there and try to force that issue right now, simply by setting the stimulus frequency to something very low, but not 0. Let's try 0.2 for a stimulus frequency. It's essentially 0. Let's see if that will go. And I've got to reset t equals 0 to do that. Okay, so we've got a force there. That's the F right there. And it is, ooh, boy, it's got a lot of frequency. How to get that? Stimulus frequency. Oh dear, it's 5.6. What's it doing with 5.6? That's not right. Let's see if we can do it with his context menu. He's made that stimulus frequency. Let's try to get that down. It's not what I want. I want something like that. Okay, let's try that. And boy, that really poops the coop there. Shoot. I guess we're going to have to do it the ugly way with the old app. And the trouble is that Apple changed things so that when I was doing this quick drawing, it makes a great gray smear across the screen, but I think you can maybe see what's going on here. Let's just try this one right here. And I just want to make it slower, but that, I think you see basically what's happening there, and that is that the response is basically in phase with the now I want to see if I can reduce the time on this thing. The time step here is a little too fast, so let me take something away from that.
Can you switch so that projects to the screen?
Pardon?
Right now you're still on the old laptop that's projecting.
Oh, thank you. This is what we should be looking at. Is that? Yeah, thank you. I look at this and I'll look at what you're looking at. Let me see if I can get the time step down on this one. That's the other thing, is that this was done from computers that were really slow. So I cooked it like mad to get it fast, and then that makes for trouble. Let's try this, and I'm going to have to come up with power a little bit to do that. No, that's not right. Let's try that. That may be too slow. Let's see what it does. Yeah, that's way too slow. Let me see if I can try for it. Gosh, that's too fast, probably. Yep. I'm having trouble getting a number between something very small and something very large. Let's try -5. And then add
something with a low power. That's too fast, damn it. It's not going to be a good day here. I'm just going to try to put it. It's a control I designed and I've forgotten how to use it. Let's try. To multiply it by something very small. That's the best we're going to be able to do. Anyway, the idea here is that the phase lag, that's this, is pretty small. And that's something that would show if I can display those pieces, and I will try to get that going. Steady state phasor. Oh dear. I don't think that's going to show very well either. But in any case, it's pretty terrible. I don't know what to do on this. I guess we just have to point it to mathematics. These guys are not going to work for us today, it looks like. We made some changes and they're bad. There's one last thing I can do here, and that is clear the browsing data. Let's completely clear it and hope that the thing that's now there is a fixed application. So let's go back here to below resonance and see if I can get it to work. Reset time, resume. Well, except for the color, that one looks pretty good. I'm going to bring the color back to white, or something close to that. Let's just make it white, that's good enough. And then reset and resume. Okay, maybe this will work. Except that right now we're talking about a stimulus frequency that's way up there. So I've got to change that. I'll try to do it.
Switch the projector back.
What's that?
Switch the projector a little back.
Which? Oh yeah. Thank you again. There we go. Okay, I want to get that darn frequency down just so I do the DC. This frequency. Let's bring that down to say 1. That'll be good enough. Reset time equals 0 and see if it'll work. Boy, that sure isn't down where I want it. I got only 1.27 now. Yeah, that's getting there. And I'm going to start the thing at 0. I think I can do that just by clicking right there. And then reset time equals 0. There we go. Okay, so there's the red oscillation is the force, and you can see the force is way slower. It's this, way slower than what the oscillator wants to run, the transient frequency, omega sub gamma, is much, much faster. And the response that you're getting is a combination of the effects of the force and what it wants to do. And it's slowly approaching, the idea is it's slowly approaching these Z steady state. Unfortunately, that's scaled wrong. It should be rigidly attached to the force vector, and it's not. So that's kind of misleading right there. But in any case, by the time we get to 15, remember that was the number of radians per second that it would be down to 5% in decay. It will shape up to be just the little bit of response, the blue line here, that we would expect from the Green's functions. That is, it would be something probably in this neighborhood right here. I think that's what we're dealing with in frequency. So we're in the DC region, and all it's doing is responding very weakly. A ratio to the force is much lower than what it will be, 15 times lower than what it will be when we hit resonance. So I guess we have to simply turn off the extra phasers because they're completely misleading as far as what's really supposed to be happening here. I'll go ahead and do that with the context control here, which you get by right-clicking. And I will unclick the interesting part of this thing right now. I think that's it. Let's see here. And I'm a little bit worried about that, too. I think I better do it with this one to make sure that it works. Let's see what it is here. I don't want that. Okay. Just start it again and see if it actually works. Okay, everything up there is right. Now, the phase lag that we're talking about here with a frequency of 1.3 compared to 6.28, which is the resonant frequency, is enough to get a slight lag behind the phaser. But while it's doing a transient, the actual response of the oscillator is all over the place. And you can see it in the phase diagram making all of these loops here as it goes, and particularly when you're close to the origin, it does a real jumpy sort of loop in the phase pattern. But as we get nearer and nearer to the 5% point, all this stuff will settle down to what we saw before, a fairly small, smooth moving, what we call steady state Green's function response. Okay. So what I want to do is walk up here a little bit, and in particular, the next one I want to look at that is when I am within gamma of the resonance frequency. So I'm not quite there yet. I'm going to be right here at not 6.283, that's 2 pi, which is resonance in radians per second at 1 hertz, right? And here I'm going to have it be 0.2 less than that, so that's the actual number that I want to try to set in this example here. So let me go over and do that. Yeah, can you see that here? Okay. let's go over the controls here and take the stimulus frequency. I'll try to see it on the board here. Up to 6.0, get it close, and then I'll go in there and just type 083 and hope that the controls work. 083. Okay, stimulus frequency. Compared with the natural frequency, which is 6.283. Okay, so that should work. Let's see what happens here. Reset to t equals 0. Resume. Okay. Now, let's see. Yeah, right. What we're going to be getting this time for phase lag is 0.206. Yeah, is that right? This is what we should be getting right here. Okay. Now remember, this plot is real versus imaginary. In other words, this is a Fourier transform phasor, if you will. It's the plotting of the blue curve at some point, this point right here, versus the green one, the imaginary plot. Okay? So those two values are the same. Okay? And they should be both the real and the imaginary. Okay? See that? 45 degrees is what we should be getting for the phase lag. And that should set in, and it's starting to already, as we approach 15 seconds, where the transient is gone, or at least down by 95%, tiny little amount. So this thing is still not quite set at 45 degrees behind the force, but it's close. Right? Does that make sense? Okay. So we're halfway up the resonant curve. This is called, this distance between that and the point on the other side of the mountain is called full width, half maximum. You'll see that expression in any study of spectroscopy. They'll be describing a spectral line or a laser output with that. This will be full width, half maximum, and then half of that, which is just what we've got right now from the center of the resonance, half width, half maximum. Because jargon is kind of terrible in this stuff. Most people kind of forget what it really means. Anyway, right now I think we're off the screen there, and this is a 45-degree angle of lag behind the force. Now, it's important to know what that really means. What does it mean if you plot the force, and this is often done, it's called a work diagram, versus the motion, and have them be 45 degrees or any phase lag at all. If you, I used to have this thing do that, but I'm not going to try that right now. But if the force is in phase with a response, that is, every time the force goes up, the response goes up, and then every time it goes down, they are just going to produce a straight line that overlaps with itself. But if the force leads the response a little bit, in other words, it goes up and then this thing goes up a little bit later, then you get an ellipse. And the area of that ellipse is the work done by the force on the system. So the phase lag is the thing that determines how much work is being transmitted to this object here by the force. But by the time you've reached the 5% and gone past it, that work is not doing anything to increase the oscillation amplitude. And that's because at that point the friction, that drag,
on this is totally consuming all the work that that force is putting into that mass, so it's immediately being wasted and dumped out the back door, so to speak, and therefore not used by the oscillator to gain amplitude. But if we had no friction, then what's going to happen is it's going to do a beating motion. And that's an important part of the transient behavior, but what we're interested in right at the moment is just in the steady state. Okay, does this make any sense? I mean, I know that Tim has probably seen a little bit of this before, so he's up on it. You making any sense out of this? A little bit? Okay. Ned, any?
A little bit.
A little bit? Can you think of a question? I mean, we can go back to basics here. I'd rather do that than just continue with just one member of the class, maybe, and Al, understanding what the hell I'm saying here. And that's the thing you really ought to learn how to do. If you're going to go to graduate school or medical school, right? You're paying, right? And you're paying a lot of money to do that. And therefore the person that's teaching it, his job is to give you the information, and you're not getting it. What did you just say there? Why is that true? That's the skill of learning right there in modern education. So yeah, I definitely want to see some questions on this, if there are any. And it sounds like there are. It's just you don't know, maybe don't know where to start asking. Cyrus, is this making sense?
Sort of. I guess my only question would be on the ball that's on the side.
On the which?
On the ball that's on the side with the force going off of it.
Let me point at the right thing. You're talking about this? Yeah. Right.
I mean, well, I guess you just answered a second ago, but I mean, like at the point where it stops moving, there's still like a force action. Yeah, I guess.
There is a little bit of a lag because of that angle, you see. So it's not a case of where here at zero frequency, this thing would have gone up and the force would be there, and then it would just follow it back and forth in phase, right? This one, the force gets ahead of it, right? It starts coming up before the ball does. It starts coming down before the ball does. So that's really what we're talking about when we're talking about this number, the phase lag. And it's a little hard to see when it's only a little bit, only 45 degrees, but that's the phase lag. I mean, it's big enough to be halfway up to resonance. So does that help at all? You see, the idea is the force is saying right now, come on up, baby, come on, come on, come on, come on up. Oh, I didn't really mean it. I'm coming down before you got up, right? You know, if you're doing a dance and trying to get some resonance, what you want to be is have maximum force here when that thing crosses the origin, right? You want to be way ahead. You want to be 90 degrees ahead. That's the best you can do if you're trying to put energy into something. And that's what we'll achieve in the next step here. That magic pi over 2. Pi over 4 is impressive, but not terribly impressive because you really don't see what this thing is doing. All of the time from here on out, it's putting work in because there's force times velocity, right? In the same direction. But before this thing gets stopped, this thing says, hey, no, I'm coming down, I'm reducing the force to 0 and even going to put a stop to you. Or try to, anyway. So this is the kind of thing I really want, before we're through with very many oscillators here, to you to understand. Let's go look at the best case. That's the next one on the chart here for our review. 6.28, or 2 pi, okay? right on. Okay, that's what we're going to be. This is the resonance that will happen. Now, the one we just had came to this point right here on the phasor diagram. This one right here has no real part at all. Real part says, I'm out of here, crashes, right? But that's while the imaginary part just keeps right on going through the peak of the real part and stops there. So the imaginary part is maxed out, while the real part is zero, okay? Well, where does that happen on this diagram, which is real versus imaginary? Well, real goes back to zero and reaches a peak for the imaginary. Okay, is that clear? From just this plot. Okay. So at that point, we're talking about a phase lag of pi over 2, 90 degrees, according to this theory. Hopefully this simulation will bear that out. But let's put it in and see if we can make it happen. Go here, and I'll get the stimulus frequency up here by simply putting a 2 right there. We were only off by 0.2, so that should bring it in. Okay? So I reset the t to 0, and resume. Is that working? There's the little phasor coming out of its original initial condition, which was 0, 0, cold oscillator being hit by suddenly by a laser at the frequency that the oscillator wants to oscillate at. Now notice what's going on here. This one peaks out just as he crosses the origin. This one peaks down just as he crosses the origin. Come on, baby, come on, right? Force times velocity maximum at the time that the force is maximum. Okay? That's what it means to be 90 degrees out of phase. Is to be applying the maximum force just as you cross the origin with a lot of speed. The most speed you're going to have. The oscillator's going to have, right? So this is the best you can do. Okay? And it's given us a response here. We're not to 15 yet, so it's still in the transient regime of building the magnitude of the oscillator that's being driven by the red vector force there. So if we get to that today, I want you to see that happening, but just with the two things against each other. Here it's some big force, that, you know, big feather, right? A big god outside of the oscillator. But when the two oscillators are just with each other, this happening is very pretty. And it's one of those things that you get it if you read a book by Feynman and maybe one or two Russian authors, but American authors, they don't think this is important. Well, they do. The ones that really know what they're doing do. It's just that they don't let their students in on it enough. Now we're reaching, since we're off the screen just now, pretty much as far as this thing can go. So we're exponentially approaching the limit. If I could have shown the transient, it would have gone to 0. It would no longer be there. All we're getting is what comes from the Green's function. Initial conditions, they don't have any trace left. Their memory has been exhausted. Okay, now what happens on the other side of the mountain? And that's, I think, particularly important for some things that are going on in physics now, but it's certainly particularly important for the work of Röntgen, who discovered X-rays. If you go to really high frequency, what happens? We won't go that high, but we'll see what is in for us as we come down the side of this giant Andes peak here.
The next stop would be the other side of pi over 4, which is right there. Okay? So if I go from the natural frequency of the oscillator, instead of being this way by gamma, I go plus gamma, I end up at another peak, but this time it's negative of the real part. Okay? And I get this same positive value for the imaginary part that I got here. You see that on the graph? Okay? That's important. That's important sort of boundary around the natural frequency that resonance is really noticeable. That is, that's the point where you're halfway to the peak. If you want to extend for some reason that boundary, you do so at the cost of having a resonance that's somewhat less than a half, you see. But the thing you should notice is that as the friction goes down, we're talking about 0.2, which for atomic oscillators is just awful. You'd never be able to work with something that was that frictional. But the idea is that this distance here, that width, is 2 gamma, that is 0.4 units on this graph here. And that's the thing that determines the uncertainty of this spectral line. And that uncertainty is due to some sort of entropy, or dirt, or friction, or something that's chaotic, messy. So, as we go to the next stop here, which is 6.483, things are going to change. We're going to go from being 45 degrees to being, and that's, I see that's a typo right there, that should be 270. I copied and pasted without change. Things have been in a rush today as we try to fix up these new applications. So I will go on this one and set in that number. That is, I'll go here on the natural frequency, instead of having 6083 or 6283, we'll now put 6483. And then go ahead and start. I'll reset the time equal to 0 and start. See how that goes. So what are we doing in the row now? Now we have, it looks like 7.7 and change for our intended phase lag. The phase lag we'll get when this thing settles down. But in the process, it's going to produce for us an amplitude that's exactly as big as what we got when we were at this point. These two are basically the same height, however you read the magnitude, or else the imaginary part, or if you don't care about the sign, the real part. The real part's now down here. Now this is an interesting place down here. You get down in here and you can make light go faster than light. And we'll talk about that later on. It'll go just as much faster than light as these guys here go slower, and you know about slower, right? Half the speed of light in leaded glass just means you have an index of refraction of 2, right? Well, when you get a half, that's when you're above resonance for whatever it is that's causing the light to refract. It's kind of magical. Hard to do, but it's something that my friend Ron Woolsworth at Harvard was very famous for getting the speed of light down to 35 miles an hour. So light would not get a speeding ticket most places. In Fayetteville, they have you a 25, I guess it's, what is it, Johnson out here? They have a 25 mile an hour zone, and they sit there waiting with their radar guns.
So light would get a ticket there, but most other places it would not get a ticket for speeding. 35-mile-an-hour light. That's pretty cool. All right, but you see now what we've got. Let's see if I can see it here. Is we've got force. Let's see if that's right. Something weird. Yeah, that's not. It should be out the back door, from where it is. It should be hanging out this way ahead of the F there. Let's see. But let's make sure I've got everything set here the way I said it was 6.4799, and it is 45 degrees, but it's not the direction I'm expecting it. Should actually be ahead. Let's see if well, let's see what happens if we go for the next, close to the next one on here. And this is where, instead of this one coming back to it was DC, this is lopsided. This drops off to zero. Actually, fourth power in the frequency drops precipitously to zero on the high side of the resonance. And that means both real part, imaginary part is practically gone here, but the real part will follow, and so will the magnitude, so that the object becomes invisible. Basically, it doesn't scatter any light, doesn't respond to it, you see. So this is how X-rays really work. This is what's going on when light goes through normal matter, normal light goes through normal matter. It is above all of the possible resonant frequencies that are in a material, whatever the material is. And if the material happens to be lead or some of the others that have big nuclear charge, and lots of really fast electrons that can respond to X-ray. If they start, you have some of those. That's called bone, right? Calcium. Okay, this is enough to show up in an X-ray, right? So you're getting a little bit of response, but it's still letting a lot through. If you have a filling, which is gold or lead, they really respond at high frequencies. So most X-rays will completely scatter, and you'll have a black image on the X-ray film, or now it's electronic screen. Okay, so what's going on there is that they're going to be here with a phase lag of pi. The phase lag will approach 180 degrees out of phase, and I'm going to have to see if we get that in the simulation here. When I crank this thing up to say 10 or something like that, that should be sufficient to make that thing almost 180 degrees. So if I bring the stimulus here, say to 10, 1, 0, well, that's not very nice, is it? That's not going to be very nice. Let's see if I can just go up here where the dragger makes something like 12 or 14. That's even more spectacular. Okay, there's a stimulus that's really faster, more than twice as fast as the natural frequency of the oscillator. Let's give that a run through here. And you can see it's faster, right? And you can see very clearly that it is nearly pi out of phase. In fact, it's 3.1. 3.14 is pi. This thing is within a few percent of pi. And there's your response. And it isn't. We haven't even reached the transient decay time of 15. Okay, it's still entertaining hopes of being active oscillator. And basically it's just oscillating at its DC frequency at first, but you can see it's dying. Okay. So that's the idea. If I get fast enough to turn the phase completely around, I can sit there with this thing on a spring and go like this, and it won't move. It'll just stay there. And you can literally do that with a spring hanging. I'm going to try that trick here, especially on a day like this where everything goes wrong. But the idea of having a real high frequency on a spring, and it's just sitting there. You see, it's kind of what we have going in a simulation here. And it looks like the Z is on the right side now. It's pi out of phase. It's in a cloud there. You can look over here and see, indeed it is pi out of phase. When this one zigs, that one zags, and when that one zags, this one zigs, and so forth, right? See the little blue curve there? That's what's left of your response function. And we're only a couple of, a little over twice the natural frequency. I'm talking about this right here, and we're probing it, about out here somewhere. Frequency scale. Okay? Now there are two ways not to give energy to things in the oscillator business. The first one is to be in phase. The other one is to be 180 degrees out of phase. One of them makes a line at 45 degrees. The other one makes a line at minus 45 degrees. Both of them are overlapping lines with no area. So there's no area in the integral of f dx. That is, there's no work being done on the average. Okay? Well, sure, you might give the thing a little jolt up, but then you take it away. It's network that counts, one whole loop. Look at the area for that. It's called a hysteresis loop if it's a complicated curve. And that's the way you judge all of the funny materials that they're making in this lab and elsewhere in the world is responding to various things: magnetism, electricity, laser, light, and so forth. Okay. Well, let's just let that one die its death and go ahead now. And we have a few minutes. I can at least get started on what is the real entree to the whole idea of waves in general, just plain old light waves. They're quantum mechanical objects too. But when you're talking about, for example, the resonance of a nuclear spin, or the resonance of an atom that's being very close to being, shall we say, excited by a laser. Any of those situations, they're just two quantum levels that, or two quantum states that are involved in a dance. And those two quantum states are going to be analogous, their amplitudes are going to be analogous to the amplitudes of the two pendulums on that little device over there. So that's what we're going to be describing now. And we're not going to have any outside force, and we're going to keep friction out of the picture for this discussions that we're doing. We're going to stay in this course as much as possible in the pure realm, where the chaos and noise and all sorts of other things don't make a mess of things. So the first thing that we consider here is that guy is sitting on the overhead projector, and kind of the model of it, but this one is longitudinal, okay, and that's a little more easy to visualize
then what's going on as I move these guys apart, I'm twisting a spring in this case. I imagine when I drew this that was the way to build this thing. It's only later I found out that's really a crappy way to build because there's so much friction with a spring that would be going across there. So we took that out and just put it right there, and it works about as good as you can expect. So this is sort of a nice picture of what you would sketch right there. And the idea is that our coordinates of motion will be some distance from an equilibrium position. That's what this little ghostly image behind there is. And if I move this one up a certain number of units, and I don't move this one up the same number of units, then the spring between them really hasn't changed, and therefore will apply no extra or different force. That is, the equilibrium position is where all of the springs are, you can say, not giving any force at all. Of course, that doesn't have to be true. It can be very compressed. It's just that that's where the thing sits, and then we're going to be measuring the distance from those equilibrium positions with variables x and y, or x1 for mass 1 and x2 for mass 2. Now, I say x and y because the quantum system that I really want you to think about is the first one that came before quantum mechanics, and that was the polarization, not of the electron or some atom or nucleus, but the polarization of light. So we're going to be talking about x and y here, or x and y, x1 and x2, as a single mechanical object with weird springs wherever they are. The effects of those springs and their lack of symmetry will have an equation of motion that's quite the same as these gadgets, and that one too, but that's an angular sort of thing. There's a transverse, if you want to say perpendicular is transverse to the space between the objects that are moving, and they're only moving in one dimension each, just like these, but these are longitudinal oscillators. That makes, that's terminology for solid-state physics. You're thinking of color centers of solids. There'll be some atom in there that's a different mass than all the others, and it's responsible for making gems have color because they resonate at some frequency in the visible. Okay. Kinetic energy, we've seen that before. And then there's a potential energy also. And how do you write the potential energy? Well, it's just good old Hooke's energy formula. Newton's nemesis, Robert Hooke. 1/2 spring constant, that's Hooke's constant, if you will. X1, okay, for this guy right here. So we're just keeping track of the energy that you get in addition to what was already in the spring sitting at equilibrium as a result of moving at that distance x1. And then there's another term for this one being moved. And it doesn't matter whether you move it this way from equilibrium or that way, you're still going to be adding the same amount of energy. This is a parabola in the x1 thing, and so is that one. And that would just be two oscillators, isotropic oscillator if the K1 was equal to K2 that we had studied for the Earth, right? This is going to make a big difference. This is the coupling term between these, that one right there. And it's going to be 1/2 K motion squared. The motion in this case is the difference between these two. So if they're not the same, or if they're opposite each other, that's going to be really big. If x2 comes in with a minus sign, that makes a plus sign here, and I get a really big kinetic energy this way. But I get the same amount of kinetic energy if I pull them equal distances from equilibrium the other way. They would start here, go that way, I get a certain term from that will be exactly equal to the one I go this way. And you can see that that can't go on forever. particularly here, I'm eventually going to crush the spring. I'm going to go beyond the limit for which this linear force law or quadratic potential law works, right? Okay, now, when we put this all together, we get a 1/2 k12 x1 squared out of this for the first term in the binomial. And so that gets tacked on right here. And also, the x2 squared contributes another one of those. So x2 squared has an extra k12 tacked in there, in addition to the k2 that it already had. And then the only thing that's left from the binomial is the coupling. So the k1, x1, x2, that kind of represents, if you think of these two as separate oscillators of energy given by their expressions, and this is the thing, this is the one that's going to transfer energy between them. So far, so good? Okay. Well, what we want to do is make a matrix form of equation of motion. And remember, we did this for superballs. It's just that this time we were worried about the potential. There we weren't, at least not until the end of the discussion, where we were having several masses fight for energy. In any case, this is actually a Lagrange expression here. I haven't told you about that. We sort of skipped over that. You can see that if I take the partial derivative of t with respect to x1, that this one, this is velocity here, that's what that x1 dot means, and this is acceleration. But if I do that, I'm going to be taking a partial derivative of this x squared right there, and that's going to give me a 2x squared, which gets rid of the 1/2, and it gives me also an x times x dot. So that time derivative of that thing gives me the acceleration times mass. So I just threw this in because later on we'll talk about Lagrange equations, but right here Lagrange and Newton equations are the same. F equal ma for number 1, F2 equal ma for number 2. But what is the force? The force is determined, and here's the physicist's definition of force: the gradient or partial derivative with respect to independent variable x1 or x2 with a minus sign. This is the force that comes back at you. If you change the displacement by a positive amount, it's going to be a negative force, vice versa. So taking this potential right here and doing that either on this one or this one's easier to do, right away I get here a modified spring constant times the distance here, and then same thing here when I take a derivative with respect to x1. And remember, this symbol means keep all the other variables constant, so I don't care about the x2, it's just along for the ride. I do care about the x1, and there is no x1 in there, so that one doesn't contribute to the first term. Clear? And I ask Marley, does that make sense? It's the partial derivative, which is, as you had raised your hand before when we talked about it, that is new here, perhaps. And I don't know if you guys have gotten into partials at calculus class or anything yet, but before you take mechanics, you're going to have lots of these, you see, so you want to be up on them. And there's not that much to it, as I'm explaining. Are there any questions about it? Could you do this? If all of a sudden it was a quiz. That's maybe the thing that you'd always ask when you're in a class. Could I do that? Right? And if you can't, hey, how do you do that? Right?
Only with a bit more practice.
Pardon?
Probably with like a bit more practice.
Well, yeah, that's the thing. Practice makes perfect. But you try to get it into useful place of your head as quickly as possible.
You see? That's what's called being smart, right? You're learning fast. You're a quick study. That's what they pay for, right? So you figure out tricks to make it easy for you to keep stuff in as permanent as it needs to be till the next exam. But I hope for people that are really doing things like medicine, whatever it is you learn should go in permanent, right? That makes you a good actor in your field. Okay, well, we're pretty close to the end, and the rest of this is a very different sort of way of doing things. First of all, we rewrite it as a matrix. That's actually not that different. I mean, we've already done something like this with our Superball problems, but the idea is that we now have a matrix that has to have something done to it in order to solve this problem algebraically. And that process is the lifeblood of anybody in any sort of oscillatory science, technology, and engineering. And that is the idea of taking a linear equation and squashing it down so there are only numbers on the diagonal. It's called matrix diagonalization. And once you've done that, you just have a series of equations which you could easily solve. In this case, they're the good old oscillator cosine sine equation. You see, each of them independent of the other one. So this becomes as important for quantum mechanics as for a farmer would be to haul water and distribute it. You don't do quantum mechanics now without learning how to diagonalize a matrix. So we're going to be studying that fairly quickly here. But I can show you just in the last minute here what it means, what it is that we're trying to do here when we think of this by geometry. I mean, the matrix can be pretty nasty if I don't have the masses equal. I will keep them equal here because that's all we need to learn for what we're going to do are the cases that have symmetry and resonance. Symmetry and resonance come hand in hand because in order to resonate with some other body, it has to be the same in some way. And particularly mass and force, definitely part of the story. So we're going to take a simple case where masses are 1, and all we care about is the k constant. The m's will go away. We'll make it easier that. And when that happens, each one of them, if you've gotten rid of that term there somehow, well, obviously if I take them away by turning that to 0, I've diagonalized things. That's not what I mean. I mean keep it there and find another way to describe this thing that takes advantage of that. So let's, just in the last minute, and we'll come back to this when we come next Tuesday. Here is a typical case that we'll have. And with K1 equal to K2, that's the plot. I call it Bear Valley. It's bare of trees. I guess the people ski bare, that is, without any clothes. Anyway, the idea is that this is northeast right here. That's the sort of the bunny slope, the easy slope to it. The place where you get the speed up and the black diamonds is on the northwest to southeast paths. Okay? So that's the way the thing is set up right now. And the reason that we have this off-diagonal thing is because we didn't pick a good coordinate system. We picked this one. We should have picked that one. That's the process of diagonalization, is to find that. And we'll show the nice techniques that work for any number of dimensions. So that's what we're after here, because once you've done that, once you've found the direction that is the same as the spring force, Kx, you're in business. Because once you get something moving on that direction, it just stays on that direction. The other one doesn't do anything.
and then you get your advanced skiing ticket and you can go on this one, you see, and it won't care about what's going on in that direction. So then all of the motions will be a sum of something doing this and something doing that. And that makes a pretty weird orbit, as we'll see. So we'll be analyzing resonance from that point of view. Okay? And it's between just two eyes. Nothing outside except for the potential, which is assumed part of the system. Okay? Well, I apologize for our lack of getting the programming working, but I think we'll get that fixed within a little bit here.